we have studied what is the ideal gas equation. This ideal gas equation tries to explain properties of gases. These properties of gases can also be explained by the kinetic molecular theory of gas. This theory is based on many assumptions. The assumptions are: the first assumption is that gases consist of large number of identical particles that are so small and so far apart on an average that the actual volume of the molecule is negligible compared to the volume of the empty space between them. With the help of this assumption, we can explain compressibility of the gas because the volume of the empty space is more, so the gases can come close to each other and thus they can be compressed. Second assumption: there is no force of attraction between the particles of a gas at ordinary temperature and pressure. Thus, with the help of this assumption, we can explain that gases can expand because there is no force of attraction between them. Third assumption: particles of a gas are always in constant random motion. If the particles of the gas were at rest, then they would occupy fixed position, and if they occupy fixed position, gases should have a fixed shape. But you all know gases don't have a fixed shape. Fourth assumption: particles of a gas move in all possible directions in straight lines. During their random motion, they collide with each other and also with the walls of the container. With the help of this assumption, we can explain that gases exert pressure as a result of collision. Next assumption: collision of gas molecules are perfectly elastic. That means total energy of molecules before and after collision remains the same. Sixth assumption: at any particular time, different particles in the gas have different speed and have different kinetic energy. Seventh assumption: though molecules have different kinetic energy, the average kinetic energy of the gas in general is directly proportional to the absolute temperature. When you plot a graph of PV against P, as you know from Boyle's law, the product of pressure and volume is a constant. So, for an ideal gas, the plot of PV against P should be a straight line. But in reality, it is not like that. As you can see from the above graph, for gases like He and H2, the behavior is different, and for gases like CO and CH4, the behavior is different. That is, there is a significant deviation from ideal behavior. Two types of curves are thus seen. In the curves for H2 and He, as the pressure increases, the value of PV also increases. In the second type, that is, in cases like CO and CH4, first, there is a negative deviation from ideal behavior. That is, the PV value decreases with increase in pressure, reaches to a minimum value, and then after that it shows a positive deviation with increase in the pressure. At high pressures, molecules of gas are very close to each other because, according to Boyle's law, as the pressure increases, volume decreases. So, the molecules come close to each other, and when the molecules come close to each other, there is a possibility that there is some force of attraction among them. So, when there is some force of attraction, they will not strike the wall of the container with full impact. Thus, the pressure is affected, or the pressure exerted by the gas in the real condition is lower than the pressure exerted by the ideal gas. If the first assumption was correct, that is, the first assumption is the volume of the gas molecules is negligible compared to the volume of the empty space. It means thus pressure of an ideal gas is equal to pressure of the real gas plus an square by v square, where a is a constant. Similarly, one of the assumptions says that volume of the gas molecules is negligible compared to the volume of the empty space. This is when the volume is high and the pressure is low. But when the pressure is high, the volume becomes less, which means the volume of the empty space is less. We cannot change the volume of the gas molecules, and here we cannot say that the volume of the molecule is negligible. So, instead of moving in a large volume V, the molecules are now forced to move in a smaller volume because here their volume is also considered. So, thus volume of the gas will now change and the new volume will now be V is equal to V minus NB, where NB is the volume occupied by the gas molecules itself. Thus, the ideal gas equation changes to P plus AN square by V square, V minus NB is equal to nRT, where A and B are constant and it depends upon the nature of the gas. This is called equation for a real gas or van der Waals equation. Thus, according to the ideal gas equation, PV is equal to nRT or PV by nRT is equal to Z. This Z is a ratio called compressibility factor which determines whether a given gas is an ideal gas or a real gas. That is, if Z is equal to 1, it is an ideal gas, and this is possible only at low pressure. If Z is not equal to 1, then the given gas is a real gas. Yes, the value of Z is not equal to 1, it is a real gas, which means Z is either greater than 1 or it is less than 1. If it is less than 1, the pressure is usually intermediate, and if it is greater than 1, the pressure is usually high. The temperature at which a real gas obeys ideal gas law over an appreciable range of pressure is called boil temperature or boil point. Boil point of a gas depends upon its nature. Above the boil point, real gases show positive deviation from ideal behavior and the value of Z is greater than 1. Below the boil temperature, real gases first show decrease in Z value with increase in pressure. It reaches a minimum value. On further increasing the pressure, the value of Z increases continuously. Thomas Andrews studied liquefaction of carbon dioxide. He plotted isotherms of carbon dioxide at various temperatures. Later on, it was found that real gases behave in the same manner as carbon dioxide. Thomas Andrews noticed that at high temperatures, isotherm look like that of an ideal gas and the gas cannot be liquefied even at very high pressure. As the temperature is lowered, shape of the curve changes and there is deviation from ideal behavior. At 30.98 degrees Celsius, carbon dioxide remains as a gas up to 73 atmospheric pressure, that is point E. At 73 atmospheric pressure, liquid carbon dioxide appears for the first time. This temperature, 30.98 degrees Celsius, is called critical temperature Tc of carbon dioxide. This is that highest temperature at which liquid carbon dioxide is observed. Above this temperature, carbon dioxide is a gas. Volume of 1 mole of the gas at critical temperature is called critical volume Vc, and the pressure at this stage is called the critical pressure Pc. Further increase in the pressure simply compresses the liquid carbon dioxide, and the curve represents compressibility of the liquid. Below 30.98 degrees Celsius, the behavior of the gas on compression is quite different. At 21.5 degrees Celsius, carbon dioxide remains as a gas up to point B. At point B, liquid appears for the first time. Further compression does not change the pressure. Liquid and gaseous carbon dioxide coexist, and further application of pressure results in the condensation of more gas until point C is reached. At point C, all the gas has been condensed, and further application of pressure merely compresses the liquid as shown by steep line. Thus, we see that a point like A in the figure represents gaseous state, a point like D represents liquid state, and a point under the dome-shaped area represents existence of liquid and gaseous carbon dioxide in equilibrium. Critical temperature of a gas is the highest temperature at which liquefaction of the gas first occurs. Liquefaction of gases, that is, gases which show continuous positive deviation in Z value, require cooling as well as compression.